Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, today in chemical thermodynamics we will be talking about work, heat and energy. To discuss this topic we have with us our subject expert Dr. Shashank Deep. Dr. Shashank Deep is Associate Professor in Department of Chemistry in Indian Institute of Technology, Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you, Amritpal. So, during the last lecture, I discussed about how thermodynamics can be used to understand various chemical and physical processes. And then we discussed about the different terms which we come across in chemical thermodynamics, like system, surroundings, walls. Today, we are going to discuss how we can change the state of the system. This is our module 2. If I take a system and I try to influence it, I can do in a two different way. One, by doing work, or second, by supplying heat. Work is generally done when an object is moved against an opposing force, while energy is its capacity to do work. Heat is generally defined as energy in transit due to temperature difference. So, when we are trying to change the system, there are only two ways we can change the system, either by doing work or by doing by supplying heat. We can categorize all energy into two different parts. One is called work and the second one is called heat. What is work? Work is your transfer of energy that make use of organized motion. So, you can see this as a system. When system does a work, these are the molecules of surroundings, there will be organized motion in the molecules of surrounding. So, when system does work, it stimulates orderly motion in the surrounding. So, any energy which induces orderly motion in the surrounding is called work. The next is your heat. Next definition, next category of energy is heat. Heat is the transfer of energy that makes use of unorganized molecular motion. So, suppose if the heat is supplied by system to its surrounding, the molecule will not go randomly motion. It will go unorganized molecular motion. So, any energy which induces unorganized motion is called your heat. So, when energy is transferred to the surrounding as heat, the transfer stimulates disordered motion of the atoms in the surrounding. So, again I would like to emphasize that all energy can be categorized into two different parts. One which induces orderly motion, and that is called work. The other category which induces disordered motion, that is called heat. Now, how does heat and work changes the system, changes the state of the system? That was first done by Joule. He did this experiment where he took adiabatic system which has a paddle wheel, and this wheel moves if you put a weight here. So, if you go this distance z, how you go? You go fast or slow? You go in a different steps, 5 steps, 6 steps, 10 steps or 1 step. But if this distance is same, what he observed is that rise in temperature is always equal if z is same. So, what he found that temperature rise was dependent only on the amount of work, but independent of how the work was performed. So, if you perform work quickly or slowly, the temperature change is going to be same. You use large or small paddle wheel, work is again going, heat rise is going to be same. So, what he thought that there is something happening in the state of the system which is independent of path taken. Now, temperature increased. What does that mean? That there is a change in state. And since work is being done on the system, so it must be equal to some energy. That is what Joule defined as internal energy. So, property of the system whose change is calculated in this way is called internal energy. And in this case, delta U is equal to W adiabatic. You must remember that we have taken an adiabatic system, it means Q is equal to 0. In that case, delta U is equal to W adiabatic. Now, change in state can happen in another way. You can raise the temperature in a different way, and that by allowing heat to flow in. So, suppose there is a system in a state 1 and there is heat reservoir. Now, you want to increase the temperature of the system 1. What you do is you bring this system in contact with heat reservoir. When you do that, heat will flow from hot object to the system, and then system energy or system temperature can be increased. Now, you see this here that we change the system by allowing heat to flow from heat reservoir to the system. In this case, work was not done, but there is increase in the temperature, and that is what we say that there is change in a state, and in that case delta U is given by Q when no work is done. So, in first case, when there was no heat involved, we got the equation delta U is equal to W. In this case, when there was no work done, delta U is equal to Q. When we combine this, we get what is known as first law of thermodynamics, that delta U is equal to Q plus W, Q plus W. Again, Q is your heat and W is your work done by the system. So, now what happened when we supplied Q or we supplied heat or work, energy is getting converted from one form to another. It is used to raise the internal energy of the system. So, heat can be converted from one form to another, but it cannot be created or destroyed. From this equation, we can say that change in internal energy of a closed system is equal to the energy that passes through its boundary as heat or work. When suppose we take infinitesimal change of a state in that case we can change this delta with this sign d. The differential of U, which is internal energy, is equal to dq, means heat supplied or heat evolved, and plus dW, work done by the system or work done on the surrounding. This is our first law of thermodynamics. Now, how to determine the sign of work or heat? So, basic principle is anything which increases the internal energy of the system will be given a positive sign, and the thing which decrease the internal energy of the system will be given a negative sign. So, suppose work done is on the system, in that case internal energy of system will increase, and so work done by the surrounding on the system is given positive sign. In the second case, when I supply heat to the system and then I can raise the internal energy of the system, and so heat supplied to the system is given a positive sign. So, again you can see here that we have two different cases. In first, there is work done on the system. So, work is being done by the surrounding on the system. In that case, internal energy will increase, and so work has been given positive sign in this case. So, W is greater than 0. In the second case, you can see that work is being done by the system. Here, since work is being done by the system, internal energy of the system will decrease. Internal energy of the system will decrease, and your W will have negative sign. W will have negative sign. Now, come to the question of heat. Again, when we supply heat to the system, then we can increase the internal energy of the system. And as I told you as a thumb rule, when internal energy of system increases, it means that it will be given a positive sign. So, in this case Q will be greater than 0. So, we supply heat, internal energy increases, and Q will be given a positive sign. When we do opposite, heat is given by the system to the surrounding, it flows out from the system. In that case, heat will be given negative sign. So, what are the three different things which we can take from the first law? First law is basically a statement of principle of conservation of energy. So, if you supply energy, it will not be destroyed, it will be converted into another form of energy. In this case, it is internal energy. Okay. So, the second thing which we came across is that when we supply heat or we do work on the system, temperature of the system increases, and that can be explained through the existence of internal energy function. So, first law gives a definition of internal energy function, and then last is the definition of heat. Heat is not energy as such, but heat is energy in transit. Means when there is a transfer of energy, that can be called heat, which induces disorderly motion in the system or surrounding. Now, let us think about what are various aspects of internal energy. What is basically this internal energy? So, internal energy is basically sum of different energies. First is translational energy of the molecule. So, molecules are in translational motion, and due to that there is translational energy that contributes to our internal energy. Again, the rotational and vibrational energy of molecule also contribute to internal energy. Molecule rotates, molecule vibrates, and that contributes to the energy part. This first and second comes into the kinetic energy. The third one is potential energy, and that is because of existence of force between two different molecules. So, if there is a attractive force or repulsive force, there will be potential energy. There will be potential energy. For example, in the ideal gas, there is no intermolecular forces. In that case, we can take potential energy as 0. The last one is the potential energy in a field due to an induced electric or magnetic dipole moment. So, all these 4 different kind of energy constitute internal energy. Now, we need to also understand what does not come into the internal energy. Internal energy does not include the translational or rotational kinetic energy of a body as a whole. So, if you take body, some system, and it is moving in one direction, that will not come under internal energy. It is only the molecules which constitute the system, their translational energy, rotational energy or vibrational energy is included into internal energy. Internal energy also does not include the relativistic mass energy equivalent, that is E is equal to mc square. And finally, it excludes any potential energy a body may have because of its location in external gravitational or electrostatic field. You must remember that in the last slide I told that potential energy in a field due to an induced electric or magnetic dipole moment is included into internal energy, but potential energy due to gravitation or electrostatic field is not included in the internal energy. As I told you that u is a function of a state variable, u is a state function, and so we can write u as a function of v and t. Why do we write u as a function of v and t? Why not p and t? We can write u as a function of p and t. Later on I will discuss that writing u as a function of v and t has its own advantage, but you can always write u as a function of p and t, that is not wrong. This is just because of our convenience, we generally write u is equal to function of v and t. And so, since u is a state function, we can write del u by del v at constant t. This type or these derivatives can be calculated for a state function, but for q and w, which is heat and work, they are not a state function. In that case, we cannot determine quantity like del q by del p or del w by del v, since it depends on q and w depends on part taken. So, from the first law what I told that du is equal to dq plus dw. Suppose I take adiabatic system. Adiabatic system is the one in which heat can flow out from the system, heat cannot flow out of the system, or heat cannot be absorbed by the system. In that case dq is 0 and then we can write du is equal to dw. So, basically change in internal energy can be defined in terms of work done for an adiabatic system. This means that work needed to change an adiabatic system from one specified state to another specified state is a work function. Since du is a state function, u is a state function and du is equal to dw, now in this case work also becomes a state function. So, w adiabatic is a state function where w adiabatic is simply u final internal energy of the final state minus internal energy of the initial state. In summary, we can change the state of the system and the way we can do it is either by supplying heat or doing work on the system. Heat and work change the internal energy of the system. Internal energy is a state function, whereas heat and work is a path function. Thank you. Students, in this module I am going to talk about work and heat. So, I will talk in detail about work and heat. What is the general expression of work? That we can calculate by looking at this figure. You see, this is a gas and gas is doing work on the surrounding. Gas is doing work on the surrounding, and that will be done when you do expansion. So, we are trying to look at the expression for the work done by the system on the surrounding. In this case, we can give dW is equal to minus F into dz, where dz is this increase in the height. So, you know that force is basically multiplication of P external into area. So, you can write dW is equal to minus P external, which is external pressure, multiplied by area of this cylinder, and this dz is your height by which expansion has taken place. We know that area multiplied by dz is equal to change in the volume, that is dV. So, work done can be written as dW is equal to minus P external dV. You can calculate work done by integrating this from the Vi to Vf. You must remember here this is P is equal to P external. So, this is the general expression for PV kind of work, that work done is dW is equal to minus P external into dV. So, when what is the work done in different processes? We can calculate that by considering different kind of processes. For example, free expansion. In free expansion, your P external is equal to 0. It means your dW is 0, and so work is equal to 0. Now, expansion against constant pressure. So, again P external is equal to constant, and if you go back, since P external is constant, you can take this out. So, you can you have simply W is equal to minus P external integration of dV between Vi to Vf, and that you can talk about that by giving W will be equal to P external into delta V. When we plot P pressure versus volume, that can be given by this area, where you can see that volume changes from Vi to Vf, and this is your P external. So, P external multiplied by the change in volume is your work done. Now, let us think about, if I try to carry out this expansion in 3 different steps, what will happen? So, suppose we are going from P1 V1 T to P2 V2 T. So, expansion is from V1 to V2. Now, if suppose I carry out your expansion in one step. So, I am going directly from V1 to V2. In that case, your P external will be P2, and so this area will give you total amount of work done by the system. Now, suppose I go from V1 to V2 in 2 different steps. So, first V1 to V1 dash, and then V1 dash to V2. So, what will be the work done? Now, you see this, we are going from V1 to V1 dash. In this case, this is the area which gives you the work. So, this is your P1 dash multiplied by change in the volume. If we again go from V1 dash to your V2, then our work done will be equal to this area. So, now you can see that total area in the second case is greater than total area in the first case. It means, if you carry out expansion in more than one step, you are going to get more work. Now, similar I can go, if I do that work in 3 steps. So, you are going from V1 to V1 dash to V2 dash and then to V2. If you go that, first step this area will give you work, for second step this area will give you work, and for third step this area will give you work. So, now you can see, if you compare from the first second, you have a more area. It means there is more work done in, if you carry out same process in 3 different steps. Suppose I carry out the process in finite number of steps. In that case, your whole area will be equal to the work done, and that is the maximum work which you can get from a system. Maximum work is only obtained when we go from V1 to V2 in infinite number of steps, and that kind of expansion is called reversible process. So, now in the reversible process, you can get maximum amount of work, and that is why reversible process has its importance in thermodynamics. So, one step you do work by the system, it will be minimum. If you go in finite number of steps, you can get a maximum work from the system. So, these infinite step processes at constant temperature are reversible, because the energy accumulated in the surrounding in the expansion is exactly the amount required to compress the gas back to the initial state. Now, you can see here that if you go and do compression, this is for expansion and this is for compression, you get this whole area. What are the important points about reversible process? These are few very important things which we may need to remember, that they can be reversed at any point in the process by making very small change, which is known as infinitesimal change. A reversible expansion or compression requires a balancing of internal external force pressure. So, now in this case, in reversible case, we can write P external is equal to P of the gas or internal. Then third important point about reversible processes, there should be a time to re-establish equilibrium after each steps, and then this is most important, there should be absence of friction. So, you can see that I have shown that if I want to take maximum work out from the system, I need to carry out a reversible process. So, for the process in chemical industry, the greater the irreversibility, greater is the loss in capacity to do work. Every irreversibility has its cost. So, we need to carry out a process in reversible manner or maximum number of steps to get maximum work from the system. Now, how can we approach reversibility? This is a general cartoon to show that how we can get reversibility. So, suppose we are carrying out expansion, we should not do in one step. The way we can do is, suppose there are several small bricks here and we take one at a time. So, you take one at a time, then there is a small expansion, then you take another one at a time, then there is a small expansion, and then similarly you can go take out one by one and you can approach towards reversibility. You should not go here from here to this point in one step. You will be losing work from the system. Not only work can be done reversibly, heat can be transferred reversibly also, and the way you can do it is by choosing temperature gradient across which it is transferred very small. So, heat may be transferred nearly reversibly if the temperature gradient across which it is transferred is made very small. Similarly, electrical charge also can be transferred reversibly from a battery if a potentiometer is used, so that difference in electrical potential is very small. Similarly, a liquid may be vaporized nearly reversibly if the pressure of vapor is made only very slightly less than equilibrium vapor pressure. Now, see the difference between your reversible process and irreversible process. If we take an ideal gas and try to carry out an expansion from Vi to Vf. In the irreversible process, the area is this and the work done is given by P external into delta V. While if you carry out that process in a reversible way, then you get whole area and your amount of work done by the system will be maximum. So, this is your let me go, what is this? So, this is your P1 V1 T to P2 V2 T, and in this case it is simply, you see, one step process, you can get V2 minus V1. This is your expansion process. If you do compression, then your, this is the area, this whole area will give you your work done, but this is work done by the surrounding, work done by the surrounding. So, in compression process, work done by the surrounding is maximum. This is for the reversible process. If we carry out a reversible process, this is for the expansion process, you get this whole area as work done. For the compression process, this is the area which gives you work done by the system. Now, there can be different kind of work. What we discussed earlier was PV kind of work. What about other kind of work? Generally, variables often form pairs such that their products have dimension of energy. The intensive member plays the role of force and extensive the role of displacement. So, here you can see there are different kind of works given: expansion, surface, elongation, electrical. They are multiplication of two different variables. One is your intensive variable and extensive variable, and the differential will give you your work done. So, for the expansion kind, intensive variable is pressure, extensive variable is volume. So, your work done is dW is minus PdV. For the surface kind of work, intensive variable is surface tension, extensive variable is A, and your gamma dA will be the surface work. For elongation, suppose you have a string and you are elongating it, force is the intensive variable, extensive variable is length, and FDL will give you differential work. For electrical work, your potential difference is intensive variable, charge is your extensive variable, and phi dq will give you different work. So, du is equal to dq plus dw expansion, which is PV kind, plus dw extra. This is known as dw extra. Extra work can include surface kind of work, elongation work, and electrical work. So, what is heat? Heat is energy in transit due to temperature difference. So, this is energy in transit, and mechanical definition is W adiabatic minus W. W adiabatic, we already know that W adiabatic is equal to your delta U. So, delta U minus W is your Q, and so this is used to define heat. What is internal energy and how we can measure it? So, change in internal energy from the first law of thermodynamics can be given by dq plus dw, and we know that dw for PV kind of work is equal to minus P external into dV. So, du is equal to dq minus P dV. If I take a constant volume process, then in that case P dV is 0 and du is equal to dqV. So, we can measure delta U by measuring heat flow between the system and surrounding in a constant volume process. However, generally our reactions takes place at constant pressure. In that case, we need to define another energy function which is equivalent to U, and that can be measured by measuring Q at constant pressure. So, now see here, differential of U is dq minus dw, and since processes takes place at constant pressure, in that case we can write dw is equal to minus P delta V. So, U2 minus U1 is equal to QP minus P V2 minus V1, and if you arrange this, QP will be equal to U2 plus PV2 minus U1 plus PV1. You must remember that PV is energy, U is energy. So, sum of these two is going to be energy, and that is called enthalpy. Enthalpy is a state function, enthalpy is an extensive quantity. and change in enthalpy is equal to heat absorbed in a process at constant pressure if the only work done is reversible pressure volume work. And the end, our summary: system does maximum work in a reversible process, and every reversibility has its cost. So, if you carry out a work in one step, you are going to get minimum work, while if you carry out that expansion in infinite number of steps, you are going to get maximum work. And finally, internal energy can be measured by measuring heat at constant volume. Thank you.
Sir, I have a few questions.
Yeah.
Sir, how heat and work is not equivalent?
Okay, so heat is energy and your work is energy, but heat induces randomly motion, right? If you supply heat, all the molecules of the surrounding or system will move randomly, while when you are doing work, your molecule will go in one direction. So, that is the difference between heat and work. Any energy which induces randomly motion can be taken as a heat, while any energy which can give your uniform or directed motion, then you can say that is a work.
Okay. So, when we talk about system and work done by surrounding, can you explain it with some examples?
Can you again tell me?
So, when we talk about system and work done by surroundings on it, can you explain it with some examples?
Yeah, for example, if you are carrying out expansion process, so expansion process, what happens that work is done by the system. You see, it is expanding. So, system is below and it is basically doing work on the system surrounding. So, in that case, work is being done on the surrounding. But suppose you are taking out a compression process, then your surrounding is doing work on the system.
Okay.
Yeah.
Sir, why is reversibility important?
If you want maximum work from the system, you have to choose a reversible process. If you carry out, I showed you from one diagram that if you carry out same expansion from initial to final, VI, VF is same. In one step, you get minimum energy. If you do in 2 steps, you get more energy, 3 steps, more energy, and when you do it in an infinite number of steps, you can get maximum energy.
Sir, why potential energy due to gravitation and electric potential is not included as?
So, potential energy due to gravitation will change energy of the system as a whole, not a molecule. And that is why molecule energy should change. That is the one of the most important criteria. Molecule energy should change. So, if a system, suppose if there is a body and this is moving like this, there is a translational motion, but that does not come under your internal energy. But if there is a system and there is a molecule inside it and they are moving in different direction, that comes under the internal energy.
Okay, so is it because it gives equal effect on all the system if system is homogeneous?
I don't think so. Yeah,
Okay.
I don't think so.
Okay. Sir, transfer of energy is called heat, and which causes it. Then what is transfer energy, sir, in that sense?
So, you see, if suppose there are two different body, one at higher temperature, another at lower temperature. Okay, when you make that into a contact, what will happen? Energy will transfer from one to another. Energy will transfer from one side to another side, and that energy transfer is called heat. That energy transfer is called heat. You must have seen, if you take two body, one is at hot temperature and another at lower temperature, if you bring them into contact, what will happen? Something will flow out from hot to cold, so the temperature is equal. So, energy will flow from the hot to cold, and that energy is called heat.
Okay, so can you please again explain to us in detail why some work is termed as negative and some work termed as positive?
This is, you see, you can give any convention, but generally what we use is SI convention. SI convention tells you that any energy which increases the internal energy of the system, any energy which increases internal energy of the system is given a positive sign, while any energy that decreases the internal energy of the system will be given a negative sign.
Sir, on that note, I would like to thank you for this very interesting discussion, and I would like to thank you, dear friends, for watching our show. I hope you have understood and have come to appreciate what work, heat and energy is all about. On that note, I would like to thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.